many of you, good morning, many of you have studied reactions and forces in an order that was somewhat set by the fact that you had not covered the concept of torques or moments yet. However, you're dealing with torques or moments from the day you start playing Crack the Whip at 3. I presume you do that. I don't know when you do that. But so this is going to be a discussion of, in effect, how in the near short term, once you get beyond adding forces, you need to free your mind to thinking about primarily torques or moments. And we have covered the idea of torque being R cross F, R, magnitude of R tagging the magnitude of F times the sine of the deflection angle, and force times orthogonal distance. And in all those, and we've finally looked at this, and that is the fact that the cross product is also the area of the quadrangle formed by a radial vector here and a force vector. So I give to you a kind of a geometric construction of reactions and moments. And so let me explain what we have here. We have a simply supported beam at C and B, and I'll see if I can sketch that up here with a marker tool, if I have to kind of do it down here. Alright, so we have a simply supported beam there. So in other words, it's got a pin joint there and a roller joint there. And applied to it at point F, which at this point is 3.37 centimeters, I guess it could be meters, it could be feet, away from it along the length of CB is a force FE down. Said force causes a moment defined by R CF cross F, which is that area there. In order for this system to be stable, a reaction force at point B, which is going to be normal straight up because it's a roller joint, it will have no x component. This force BG must react to force FE so that the moments are equal and opposite, and the moments are described by the area. So watch what happens in this dynamic model as you go ahead and change either the angle here. We're going to do a typical maximum moment. You know, the deflection angle here is 270 more or less. There, it's right there, or minus 90, and you see that these areas are equal. So depending on how that force, if that force becomes more or less collinear with the beam, you've got basically just compression and tension. You don't have any reaction to force in the y direction, and you have that kind of laid out here. You can notice how this reacts. In effect, that is a large part of structures. If you do this based on the rule of superposition for every single force, you will determine the reactions. And you can do the same thing about B to get the reaction at C, though we're not going to do that here. So let's see how this was constructed so you can get used to this engine. I'm going to turn on, click over here, display, show all hidden. Let's see how we constructed this. Pretty complicated. Well, here's how we did it. We constructed a circle diameter of 12, right? 6 at the radius here. That is the equation for it. We constructed a point F on CB, which was more or less constrained. The term is constrained to CF. So it's some distance along F. And you can notice as you pull this along, it's locked into CF. We constructed some perpendicular lines to this by picking an arbitrary point and constructing a perpendicular line. Then constructing a parallel line to that perpendicular line through B. Here, constructing a parallel line to CB through E, and a parallel line CD to FE. So you do a lot of parallelism, if you would, here. And finally, you have to then calculate a number so that this moment here is at equal and opposite to this moment. So you need to take this area here divided by this distance here and then draft a circle whose radius is determined by that ratio of the area here to the distance there. Now this works, and it is only designed in this sheet for a 90-degree reaction at BG, as would be come about due to a roller joint there. So that's the construction. Once you get the kind of theme of this, you can realize how much of algebra is geometry, and how much of geometry is algebra, and how much of trigonometry is algebra, etc., etc. And so once you get these things all laid out, all you do to hide them is you kind of can click through, click, hold the shift key, so it doesn't get so confusing. And go to display. Sure. Looks like it did most of them. And then you have essentially that description of a reaction moment. Now, you're going to see once you grab this, this is about sketching it and getting approximate answers generally. It's still best done and most rigorously done by matrices, so that you can get kind of laid out for 3D and not really have to worry about or think about matrices as being these kind of odd things that are just an esoteric concept we cover once in engineering using the standard IJK. So later on you can see that you can actually, I don't know if you can actually measure this, but you can actually measure here. You can measure its length and its angle and its slope and calculate. So you have the length there, and you can also measure interesting. I thought you can measure, if you measure its length, you can measure its slope, and based on this slope you could convert this to x's and y's. If you remember, the slope is the tangent, I'm sorry, the slope is the tangent of the angle. So thanks for listening. We'll play around with this on and off throughout the semester and be building a number of these models. This again is Geometer Sketchpad. I'm sure this one is put out. I just am going to be going through a little bit of development so you can kind of learn to do this with a compass in your hands or with a piece of software if you can get a hold of it. All of this can be done with AutoCAD or Inventor constraints as well, I believe. So thanks for listening.